Hi again. This is Professor Van Hul about computer vision, and obviously, in order to get computers to assess images and their content, we somehow have to get those images first. And this is the basic topic of today. So, the acquisition of images. This figure we saw before. So, we have objects in the world. We have an illumination source indicated by that sun, and then the incoming light will hit the surface of the objects, and part of that light will get reflected into the camera. Today we will talk a little bit about illumination and how we can actually tweak it to make our job for image analysis simpler, and then we will also talk about how this image capturing part of the camera actually works. So we talk about illumination, and then we talk about cameras. First part, the illumination, and especially ways in which we can actually adapt that illumination to simplify the processing of the images. So often a problem in, for instance, visual inspection can get simplified a lot if you are careful on how we set up the illumination. So well-designed illumination often is actually key. Here we'll now give a number of examples that we will discuss, like backlighting, directional lighting, diffuse lighting, polarized lighting, color lighting, structured lighting, and stroboscopic lighting. So we will quickly run through all of those, explaining why they may simplify the image processing problem. First of all, backlighting. Basically, the idea of backlighting is to provide illumination from behind the object. So you would have like the illumination, then the object, and then a camera looking towards the object. And the goal of forming back illumination is to get this silhouette image of the object. So to have more or less a binary image. Black for the object, white for the background. And by the way, often behind the illumination source and the object you apply a diffusion layer to make sure that the illumination is spread over spatially. Here we see an example. It's about inspecting bottles, and often this is a rather subtle inspection task because there may be small cracks in the bottle, and you want to detect those before leasing the bottles out again to be refilled. Now what will happen is that if you have that kind of back illumination that you see there, this homogeneous white illumination in the background, you have the bottles moving in front, they will be all black to the camera, except when there is a crack. So when there is a little crack, that crack will probably give a very bright reflection towards the camera because the orientation of the glass is so abnormal. And that is the giveaway to disregard those bottles with such bright illumination within the silhouettes. And you will see that inspection system at work. So bottles pass, and as soon as the camera notices a bright spot inside the silhouette, it will get rid of that bottle. So this inspection goes very, very fast. The processing is made easy because this is template of the bottle silhouette. As soon as something too bright appears within that silhouette, that bottle has to be removed. So this is illumination actually replacing what otherwise would be a very complicated visual analysis. Then directional and diffuse illumination. Directional illumination would mean that you have illumination coming from a very particular angle. And that will typically generate rather sharp shadows It may also generate specular reflection at places of the object where the orientation is in the mirror symmetric orientation, and that may help for crack detection again. And shadows and shading yield information about the shape. So that's one form. You may actually go after these specular reflections where the orientation of the surface is abnormal. Then you can also take the opposite view, and you can go for so-called diffuse lighting. This means you try to get the lighting from everywhere. So you try to get omnidirectional lighting from all orientations coming in and falling onto the surface. So this illuminates uniformly from all directions. It prevents sharp shadows and large intensities because there's so much diffuse lighting that the reflective lighting, the specular reflection, is in comparison not that strong anymore as before under directional lighting. So all directions contribute extra diffuse reflection, but contributions to the specular peak arise from only the very particular direction that corresponds to the mirror condition. So in that case, in fact, you avoid the dominance of some specularities over the diffuse reflectance. Here's an example of this directional illumination coming in. Suppose you have a surface on the bottom and there's a scratch, and scratch is indicated here with this little indentation. Now, suppose we illuminate from the left, as you see, light falling in onto the surface, and then we can put the cameras at different positions. We can put the camera in the position that would correspond to the mirror direction if you would look for the normal surface, so the horizontal surface. Then that camera on the right would be in a mirror position. So the normal surface would reflect a lot towards the camera because the camera is looking into the region of specular reflection. So it gets a lot of light except for the scratch, which has abnormal orientations and does not direct its light towards the camera so much. So in that case, and you see it for the image that is shown on top, you would have bright everywhere except at the scratch. Here in between, we have put the camera also in a different orientation. This is an orientation that does not correspond to the specular direction for the normal surface. So now the opposite will actually happen. And that is shown also with the image on the top left. So all the correctly oriented surface, the horizontal surface, doesn't reflect too much towards that camera because it will mainly reflect in that mirror reflective direction. But if you have a scratch, of course, that has all kinds of orientations. Also the orientation that would correspond to the specular reflection direction for that particular camera on top. So on the scratch actually reflects specularly also towards that camera. So what you would see in that case is a bright scratch in a dark, correct environment. So it's a bit like looking for the scratch in two different ways. This so-called bright field, where the normal surface would heavily reflect, but not the scratch, or the dark field for the camera above there, where the normally oriented surface would hardly reflect, but the scratch will. Okay, we will now show an example where such inspection happens. So this is about dark field and bright field, and we have this slide explaining a little bit more. Okay, suppose you have this PCB board. This scratch here should not happen, so that has to be detected before you start to put all kinds of chips on top of that PCB. You want to detect the flaw early on. And now we will show, as we change the orientation of the plate, how the scratch goes from darker than all the rest. So this camera now initially is more in the kind of bright field orientation. And then the scratch will actually become brighter than the normal surface. So that's when we have a relative orientation that corresponds more to the dark field condition. So here we go. So originally the scratch is darker than the background. We rotate the plate to correspond more to a dark field position for the camera, and then the scratch actually becomes brighter, as you could just see a moment ago. Okay, this is about directional lighting, where you play with the direction of incoming light in the hope of having a specular reflection for the flaws that tells them apart from the normal surface. We also mentioned omnidirectional lighting, this uniform or diffuse lighting. And here you see an example. So this would be a case where you have illumination coming in from multiple orientations. But then we will also show that if you choose the illumination badly, that you get problems with this very bright specular reflection. So this is okay. Here you could inspect this PCB, but if the orientation gets in the wrong orientation, like here, so this would be like a case where you have very strong directional lighting, and you see that you have all these bright spots that make inspection virtually impossible. So again, better to have omnidirectional reflection, omnidirectional illumination in this case, than having this very particular diffuse reflection. So again, a matter of choosing your illumination a bit wisely in order not to necessarily complicate the inspection problem. Okay, so diffuse reflection or directional reflection, these are things we can easily relate to as humans because, of course, we can see that ourselves. We have talked about polarization of light, linear polarization of light before. And we have also mentioned then that polarization, the polarization state of light, is something humans cannot see. But that doesn't mean we cannot use it. And here we'll see two examples of how the polarization of light can actually be used to simplify inspection problems. We have these two forms of usage. The first, to improve the contrast between Lambertian and specular reflections, number one. And then number two, also to improve the contrast between dielectric material and metals. Okay, before we can talk about polarization, we have to explain a bit more about how polarization works. Actually, by now we have rather cheap film that will polarize light. And you see that indicated here. So on the left-hand side, you have the illumination source, then you have this polarization filter called here the polarizer. Okay? So on the right-hand side of that polarizer, only light with a certain polarization direction will come through. So it will linearly polarize the light in the direction of the arrow. And then we put a second polarizer after that. So this is called the analyzer. And then on the right-hand side, we would look through these two different filters, two different polarization filters. Basically, they are the same type of filters. Both the polarizer and the analyzer are just two linearly polarizing filters. And now, if they are not perfectly aligned, so if the direction of polarization is not perfectly the same, but makes an angle theta, as indicated in this slide, what you will actually get through of the incoming light I0, that's the light at the very left falling onto the first filter, the polarizer, is I0 times cosine square theta. And that's the light that we see on the right hand side. So that's what's coming through here. So what we see is that if the two filters are aligned, most of the light gets through. But then, as you cross the two filters more and more, so the angle starts to increase, you get less and less light on the right hand side. So under angle 0, what you see is I0, and as the angle increases, less and less light gets through. If theta is 90 degrees, pi over 2, the cosine drops to 0, and you get no light whatsoever. Now, I have to correct a bit what I said before. I0 is actually just the light that you see pass through under 0 difference, if theta is 0. And typically, it's already, in fact, less than the light that you have been shining onto the polarizer. In fact, the use of polarization easily gets you to only half the illumination intensity that you started off with. So I0 will already be less than what you were actually shining onto the polarizer. But you see that if you increase theta further, you will lose even more light. Until you hit pi over 2, then you have a complete black image getting through. So, polarization will always cost you light. That's the pain, that's the price you have to pay. If using polarization, you will lose light. But now we'll see how we can actually use it in order to simplify inspection problems. So the first example is to improve the contrast between Lambertian and specular surfaces. So here's the setup. We have this surface here, may consist of multiple materials, some specular, some diffuse. We start with light shining onto the polarizer on the left. We see its preferred direction of polarization. So after the polarizer, the light will have been polarized with that orientation. That polarized light hits onto the surface, is getting reflected back to the camera on the right. But between the surface and the camera, we have placed this second polarization filter, analyzer, and we see the orientation of that analyzer is crossed. So now what will happen is the following. If you have a specularly reflecting part of the surface, that will keep the orientation intact. Now the orientation of polarization. The orientation of polarization being the one along the line on the left. It will get completely blocked by the analyzer because it makes an angle of pi over 2 with that light. So specular reflecting surfaces, although normally they would be extra bright, are now being completely blackened out by that couple of polarization filters. On the other hand, if you have a diffusely reflecting part of that surface, it will reflect light with all different kinds of polarization angles. So even if the incoming light is polarized, the reflected light at a place of diffuse reflection will no longer be polarized. It will have all kinds of orientations, meaning some of that light would also get through the analyzer. So a diffusely reflecting part will now be bright in comparison to the specular reflecting part of the surface, for which all the reflected light gets blocked. And here we have an example of this. We have this specular copper material in the center on top of this diffusely reflected back of the plate. And if you bring into place the polarization filters, as we just did, you see that all the diffuse parts are now the brighter ones, although originally they may not have been. So if you have to somehow detect what is copper and what is the diffusely reflecting part or the central part of this PCB plate, it's a bit difficult. At some parts, the background is brighter. At other parts, actually, the copper is brighter. But if you apply polarization, it's the same everywhere. The diffusely reflecting PCB becomes brighter than any part of the copper. And you see that happen. I will repeat now this upon the application of polarization. So now we see the back plate everywhere is brighter than the spectrally reflecting copper at the top, actually. Okay, that's one application, making a distinction between diffusely and spectrally reflecting light. A second application would be to get a contrast between dielectrics and metals. And how does that work? Well, remember this slide. We have shown it in the first lecture, actually. It shows you the level of reflectance of light when falling in onto a surface under different angles. So the angle of incidence you find here on the abscissa. So 0 degrees would be impinging orthogonally to the surface, 90 degrees coming very, very sharp onto the surface. And we saw that in case of dielectrics, we have special behavior for one of the components of the incoming light, the power component. It gets suppressed almost completely around the so-called Brewster angle, which typically is about 60 degrees. So if you have a dielectric, you have this type of behavior. So if you come in with only parallel light, under the Brewster angle, nothing will get reflected. So that will be pretty dark. On the other hand, if you have a metal, we saw this behavior. So we have very high reflectance under all angles. What that now means is that if we make sure we polarize the light, we shine under the Brewster angle, that what gets reflected is mainly coming from metals, because nothing much will come back from the dielectrics. That component died. So here's the setup. So you shine light onto that surface, more or less under the Brewster angle, as said, about 60 degrees. Okay, of the reflected light, the parallel angle will have been suppressed already. So now there is only the perpendicular angle. Only that light survives. But it's blocked by a polarization filter that does not let through the perpendicular angle, but only the parallel one. Meaning, if you have light that hits dielectrics under the Brewster angle, only the perpendicular angle survives, but then gets killed by this polarization filter in front of the camera. So all the light coming back to you should come back from metals, because from dielectrics nothing can come back. Here's an example. Again, if you would like to inspect this kind of image, a PCB, it will be complicated. You have areas on the background that are darker than the metal, and also that are brighter actually. So it's a kind of complicated situation to make sense of this. But if you apply the polarization filter that we have just shown in the previous slide, all of a sudden this problem becomes so much easier, and all the bright spots are coming from the metal, and the entire background directly get dark. So here we go, introducing polarization, and the problem becomes so much easier now. All the metal being bright and the dielectric or the PCB board in this case, becoming dark. Okay. Another trick is to use colored lighting. So sometimes you are looking for a particular color in the scene, you know it in advance. So in that case, you can apply light of the same color so that the part that you're looking for reflects more of the light. Here's an example. Suppose you are looking for the red label. So if you reflect with red light, it becomes almost like a binary problem. And the red label will stick out compared to the green parts of the scene. So with red light, it's much easier to find that label. Okay. Again, as we can see color, of course, that's easy for us to understand. Then there are more forms of controlled lighting, one of them being structured lighting. So that means you have a pattern of light. Could be spatially or temporary or both modulated. So you can have a pattern spatially or you can change light over time. And this is very popular when it comes to getting the shape, the three-dimensional shape of objects. And we will talk about that a bit more in the future for the lecture about 3D capture. You could also have stroboscopic lighting, which means this is temporarily modulated light, where you only flash light during a very short time. Now, you have to make sure, of course, that your image is formed with enough photons coming in onto the camera. And one way would be waiting so that you get enough photo collection. But if the object is moving fast, that generates a blur, which is not good. But alternatively, you can make sure there are enough photons to build the image by just illuminating with very, very bright light, but during a very short amount of time. That still gives you enough photons to have a good quality image, but the blur will go because the actual integration time of the camera has now been artificially altered to the time of this stroboscopic light. And here you have an example. So this would be the kind of image of a PCB board passing very quickly beneath a camera. So you see all the blur going on. That's not the kind of image you would like to inspect. But if you now have stroboscopic light, so very bright pulses of light during a very short time, that helps you to build a sharp image instead. So we have dark, then a small pulse of light, very bright period, and then going back to dark. And you see that the images now are much sharper. So that's kind of an artificial way of controlling the integration time of the camera, the time used by the camera to collect photos and build an image. Okay, here we see an example of agricultural produce inspection where several of these illumination techniques are used. So this is an inspection. It has to inspect, in this case, these beans and all kinds of material that does not have to go there, like twigs and so on. They all have to be removed. You see how fast the produce is flowing out of this machine, how fast it has to be inspected. Initially, it was a manually inspected machine. Okay. So now the idea is to do that inspection automatically. So initially, I said, people would inspect. And they would, of course, do the best they could. But yeah, you can imagine how boring this type of job is if you have to stare for hours to that machine. So they let the machine run for about 24 hours and then consider what was left to pass through as okay by the human operators. And we'll soon see the result. So what in a normal shift would get through as being okay beans. And they are not quite okay, right? So you see a lot of rodents here on that table. They were all passing through within a single shift of manual inspection. So instead of that, machine inspection can do a much better job because it has this unabated attention. And rather than having all the manual inspection going on, now the machine would decide what to let pass and what not. Well, as part of this, there are a number of tricks that we have just seen that are used in these type of machines. One is polarized lighting. So usually these vegetables will be washed before they are put through the machine, so the vegetables are quite wet. Polarization is used against specular reflection, as we saw. And second thing is, one inspects with green light, the light of the beans, of the okay material, so that anything of a different nature will tend to be darker. And that helps in making a very simple check, bright enough or not, to eliminate all the false material. And here you see the false material coming out, all the dirt being eliminated at very, very high speed. All right.